Hello everyone and welcome back to my channel. This is the A+ Tutor. Today we're going over factoring polynomials using the rational root theorem. The rational root theorem states if the polynomial f of x equals a n x to the n plus a n minus 1 x to the n minus 1 all the way to a1x and a0 has integer coefficients, every rational zero of f of x has the form p over q, where p is a factor of the constant term a0 and q is a factor of the leading coefficient an. So what does that mean? A rational number is just any number that can be written as a fraction. These are both positive and negative numbers, so numbers like 1, 2, 1/2, -3/4. These are all rational numbers. So what we're doing when we use the rational roots theorem is we're finding our possible zeros for our polynomial, and then we'll also be able to identify what the actual rational roots are for our polynomial. A graph of a polynomial may look something like this. With the rational root theorem, what we're able to do is identify our rational roots of our polynomial, all of our possible roots, and then the actual roots. And our roots are just our x-intercepts, like these 3 points here. Those are our rational roots. We have turning points, other turning points in our graph, like here and here and here, but these do not have rational roots. These turning points are going to be other values that we cannot find using the rational root theorem. The rational root theorem will always give us our possible x-intercepts for our polynomial, and then we can solve to find out what the actual x-intercepts are and possibly factor our polynomials as well, which is the goal of today's video, to factor polynomials using our rational roots theorem. So let's take this theorem and work through it with an example so it can make a little bit more sense. Let's take the example, f of x equals 2x to the third plus x squared minus 4x plus 1. So the first thing we want to do is identify our p and our q. Our p is our constant term. Your constant term is always your term that does not have a variable attached to it in your polynomial. This usually will be your last term in your polynomial, but if your polynomial is out of order, then it's the term that does not have a variable tied to it. In this case, our constant term p is equal to 1. And then our q is our leading coefficient. The leading coefficient is typically the first number that we see in our polynomial. But if our polynomial is out of order, the number that has the variable with the largest exponent, that number is your leading coefficient because that entire term is your leading term for your polynomial. So in this case, our leading coefficient is 2. So then the next thing we want to do is find all of our factors of p and q. So the factors of your number are everything that we can multiply together to get that number. Our factors for these two numbers are pretty simple, but if we had something like 15, our factors would be 1 and 15 and 3 and 5. We also want to make sure we are taking into account the positive and negative value of those factors. So our p is just positive and negative 1, and our q is positive and negative 1 and 2. So now we want to look at all possible combinations of these factors. So we would have positive 1 over positive 1, positive 1 over negative 1, negative 1 over positive 1, and negative 1 over negative 1, positive 1 over positive 2, positive 1 over negative 2, negative 1 over positive 2, and negative 1 over negative 2. So when we simplify this, all of our possible rational roots are going to be positive 1 over positive 1 is 1, positive 1 over negative 1 is negative 1, negative 1 over positive 1 is negative 1, but we've already taken that into account, so we don't need to write that again. And negative 1 over negative 1 is positive 1, so again, we've already taken that into account, we don't need to write it again. Positive 1 over positive 2 is positive 1/2. Positive 1 over negative 2 is negative 1/2. Negative 1 over positive 2 is negative 1/2. We already have that listed. And negative 1 over negative 2 is positive 1/2, which again, we already have. So these four terms here are all possible rational roots for our polynomial. If there is a 0 for a polynomial that is a rational number, it's going to be one of these four numbers or a few of these numbers, right? We may have multiple rational roots for this function, but we want to see which ones they are. We're going to use these terms to factor, which takes me into step 3, which is finding these zeros using division. There are two ways we can do this when I say division. You can either do long division or synthetic division. I prefer synthetic division, so that's the way I'm going to show in this video. I think it's a bit more straightforward and a bit easier to use. If you prefer long division, there's no wrong way to do it. If we both get to the same answer, that's great, but I will be showing all of these examples using synthetic division. By finding the zeros using division, we're able to factor this polynomial completely. So as much as it can be factored, we're able to do that by breaking it down in this first step here. All right, so let's start with x equals 1. When we do synthetic division, we'll put our x value inside our little house off to the side with something blocking it. And then we'll write our coefficients for all of our terms in our polynomials in a line across. So we have 2, 1, -4, and 1. We start by bringing that first term down. The pattern for synthetic division is multiply our x value in our term and then add down. So 1 times 2 is 2, we'll bring that up. 1 plus 2 is 3, we add that down. 1 times 3 is 3, we bring that up. -4 plus 3 is -1, 1 times -1 is -1, and 1 minus 1 is 0. So this is our check right here. We want to see if we do get 0 as our last term, which is our remainder. Whenever we get 0 as the remainder, we know we found a 0 of our function. That 0 tells us it's a 0. This means that x minus 1 is a term for our polynomial, and we can rewrite our original polynomial as x minus 1 times 2x squared plus 3x minus 1. When we do synthetic division, the numbers we get at the bottom become our new coefficients for our polynomial. The last step in this process is to finish factoring if possible. In this case, this polynomial cannot be factored further, so our final answer and our final factored form for our polynomial is x minus 1 times 2x squared plus 3x minus 1. So just to walk through this again, we start with our p and our q. Our p is our constant term, the term at the end, and our q is our leading coefficient, that number at the beginning. We want to find all of our factors of p and q to find all of our possible rational roots. And then we're going to go one by one, use division to identify which one is our root. When we have a remainder of 0, that means we found our root. So now we can rewrite our polynomial using that root and whatever we have left over, and then continue to factor from there if possible. So let's look at some examples of factoring these polynomials using the rational root theorem. The rational root theorem tells us first to identify our p and our q. So remember, our p is our constant term, which is the last term in our polynomial, usually the last term. It's the term that does not have a variable attached to it. And our q, which is usually the very first number we see in the polynomial. So in this case, our p is -1 and our q is 5. So when we look at p over q, we're looking at -1 over 5, but that negative really doesn't matter because we want to consider all possible factors and the positive and negative values of those factors. So really, we have positive and negative 1 and positive and negative 1 and 5 because all of our factors of 5 are 1 and 5. So our possible rational roots are positive 1 over positive 1, positive 1 over negative 1, negative 1 over positive 1, negative 1 over negative 1, positive 1 over positive 5, positive 1 over negative 5, negative 1 over positive 5, and negative 1 over negative 5. Simplifying this gives us 1, negative 1. We already have negative 1, and we already have positive 1. Negative 1 over positive 1 is negative 1. Negative 1 over negative 1 is positive 1. So continuing on, we have 1 over 5, negative 1 over 5, and then these two are also already represented. So now what we want to do is we want to start to work through these possible zeros and see which one is the actual zero for our polynomial. Let's start with x equals positive 1. So using synthetic division, we have 5, negative 11, 7, and negative 1. We'll bring down our 5. 1 times 5 is 5. Negative 11 plus 5 is negative 6. 1 times negative 6 is negative 6. 7 plus negative 6 is positive 1. 1 times 1 is 1. Negative 1 plus 1 is 0. So that's exactly what we're looking for. We want a remainder of 0 here at the end. So that means one of our factors is x minus 1, which is great. The rest of our polynomial becomes 5x squared minus 6x plus 1. So now we're going to finish factoring if it's possible. Looking at our polynomial here, which is 5x squared minus 6x plus 1. This is a quadratic function, so we can factor this the way that we would factor quadratic functions. We'll take our a and our c term, multiply them together, we get 5, and we want to look at the factors of 5 that will add to give us negative 6, which is 1 and 5. That's exactly what we're going to use. So we can expand this into 5x squared minus 5x minus x plus 1. Negative 5x minus x will give us negative 6x. So now let's factor by grouping. Break this in half. Factoring the first half of our function lets us pull out a 5x, and we're left with x minus 1 on the inside. Factoring our second half of our function lets us factor out a negative 1, and we're left with x minus 1. So now our fully factored form of this quadratic here is 5x minus 1 times x minus 1, and then we'll bring back our x minus 1, meaning our fully factored form of our original polynomial is x minus 1 times 5x minus 1 times x minus 1. Or we can group those x minus 1 terms together and get x minus 1 squared times 5x minus 1. Now let's look at another example. We have f of x equals 3x to the third plus 11x squared plus 5x minus 3. So step 1 is identify our p and our q. Our constant term, or our last term in our polynomial, is p, the number without a variable attached to it. And our q is our very first number in our polynomial, the leading coefficient. So in this case, p over q is going to be our 3 over 3, and we want the positive and negative factors of each. So this is positive and negative 1 and 3, and positive and negative 1 and 3. all of our possible rational roots are positive 1 over positive 1, positive 1 over negative 1. I'm going to skip our negative 1 over positive 1 because we know we're going to take care of the negative case here. Then we also have positive 3 over positive 1 and positive 3 over negative 1. Then we have positive 1 over positive 3 and positive 1 over negative 3. So skipping some of those extra factors, we know all of our possible rational roots are going to be positive 1, negative 1, positive 3, negative 3, positive 1/3, and negative 1/3. So now let's work down the list and see what our potential x value is, starting with x equals 1. So we'll set up 1 and set up our synthetic division. All right, so let's bring down our 3. 1 times 3 is 3. 11 plus 3 is 14. 1 times 14 is 14. 5 plus 14 is 19. 1 times 19 is 19. Negative 3 plus 19 is 16. This is not one of our factors because we did not get 0 as our remainder. So that means x minus 1 is not a factor, and we need to move on to the next one in the list. So now let's try x equals negative 1. We have to repeat this process as many times as it takes for us to find our x value. Sometimes we find it on the first try, like we did in the last example. Sometimes it takes us more than one. But this is one of the only ways we can identify what our root is for this polynomial. So we'll follow the same process. Bring down our 3. Negative 1 times 3 is negative 3. 11 plus negative 3 is 8. Negative 1 times 8 is negative 8. 5 plus negative 8 is negative 3. Negative 1 times negative 3 is positive 3. Negative 3 plus 3 is 0, and that's exactly what we're looking for. So we know one of our zeros for this function is x plus 1 equals 0. And we can rewrite this function as x plus 1 times 3x squared plus 8x minus 3. Now, let's see if we can factor this quadratic function further. So we have 3x squared plus 8x minus 3. We'll do our a times our c, which is negative 9. Well, the factors of negative 9 are 1 and 9, and 3 and 3. We need 8, so we'll use 1 and 9. This becomes 3x squared plus 9x minus x minus 3. 9x minus x add to give us 8x, so this is correct. When we factor by grouping, we'll break this up in 2, factor our first half, which will factor out a 3x. We're left with x plus 3. Factor out a negative 1 from our second group, left with x plus 3. So our fully factored function here is x plus 3 times 3x minus 1. We need to bring back our first root that we found. So our fully factored polynomial becomes x plus 1 times x plus 3 times 3x minus 1. And that is our final answer. For our next example, we have f of x equals 2x to the third plus 9x squared minus 2x minus 33. Our p is our constant term, which in this case is 33, and our q is our leading coefficient, which is 2. So we want all the factors of our p over q, which is our 33 over 2, which is going to become, on our numerator, we'll get positive and negative 1 and 33 and 3 and 11. In our denominator, we'll get positive and negative 1 and 2. So now let's figure out all of our potential values. So first, with our 1, we'll have positive and negative 1 and positive and negative 1/2. Then if we look at our 3, we'll have positive and negative 3 and positive and negative 3/2. Our 11 will give us positive and negative 11, positive and negative 11/2, and 33 gives us positive and negative 33, and positive and negative 33/2. So it's possible that we may have to touch on every single one of these values to find our rational root. So let's start working our way through, starting with x equals positive 1. 1 times 2 is 2. 9 plus 2 is 11. 1 times 11 is 11. Negative 2 plus 11 is positive 9. 1 times 9 is 9. And negative 33 plus 9 is negative 24, which is not 0. So we know that x equals 1 is not a possible term, and positive 1 is not one of our rational roots. So let's try negative 1. We'll bring down our 2. Negative 1 times 2 is negative 2. 9 plus negative 2 is 7. Negative 1 times 7 is negative 7. Negative 2 plus negative 7 is negative 9. Negative 1 times negative 9 is positive 9. Negative 33 plus 9 is negative 24. Again, not 0, so this is not our root, and we know that neither positive nor negative 1 is a possible value. I'm going to skip 1/2 just because it is slightly easier to work with. I like to work with the smaller whole numbers before I jump into the fractions. So you always want to try and be more efficient, meaning you don't want to waste a lot of time trying out every single one if it's going to take you a long time to solve one. If you can find it because you can work through a problem a lot faster with a number that's a bit easier to work with, like a positive or negative 3, then go that route before having to look at your fractions or your larger numbers. That way, you can save yourself some time in the process. So instead of looking at my 1/2, I'm actually going to look at x equals positive 3. So we'll bring down our 2. 3 times 2 is 6. 9 plus 6 is 15. 3 times 15 is 45. Negative 2 plus 45 is 43. 3 times 43 is 129, and negative 33 plus 129 is 96. This is not 0, so we know that this is not a solution. So now let's try x equals negative 3. We'll bring down our 2. Negative 3 times 2 is negative 6. 9 plus negative 6 is positive 3. Negative 3 times 3 is negative 9. Negative 2 plus negative 9 is negative 11. Negative 3 times negative 11 is positive 33. And negative 33 plus 33 is 0. So we found our solution. We know that x equals negative 3 is our solution, which means one of our terms is x plus 3 equals 0. So our polynomial becomes x plus 3 times 2x squared plus 3x minus 11. So now let's see if we can factor the rest of our polynomial. So our a times our c is 2 times negative 11. This is equal to negative 22. The factors of negative 22 are 1 and 22, and 2 and 11. None of these factors add up to give us 3. So this polynomial cannot be factored further. This means our final answer for this factored polynomial is going to be x plus 3 times 2x squared plus 3x plus 11. That is our fully factored form for our polynomial. Our next example, f of x equals 2x to the third minus 23x squared minus 16x minus 2. Our p is our constant term, which in this case is 2, and our q is our leading coefficient, which is 2 also. So p over q is going to be all of our factors of our 2 over 2, which will become positive and negative 1 and 2 over positive and negative 1 and 2. Our possible factors then are going to be positive and negative 1 over 1, which is 1, positive and negative 1 over 2, or 1/2, positive and negative 2 over 1, and then we also have positive and negative 2 over 2, which is just 1, so we don't need to include that here again. Now, let's work through our possible factors to find what our actual factor is for our polynomial, starting with x equals 1. So we start by bringing down our 2. 1 times 2 is 2. Negative 23 plus 2 is negative 21. 1 times negative 21 is negative 21. Negative 16 plus negative 21 is negative 37. 1 times negative 37 is negative 37. Negative 2 plus negative 37 is negative 39, which is not 0, so 1 is not a factor. Let's look at negative 1. 2 times negative 1 is negative 2. Negative 23 plus negative 2 is negative 25. Negative 25 times negative 1 is positive 25. Negative 16 plus 25 is positive 9. Negative 1 times 9 is negative 9. Negative 2 plus negative 9 is negative 11, which is not 0, so it is not a factor. And we know that neither positive nor negative 1 is a solution. In this case, let's go in order. Since we only have 6 possible values, let's go in order. Let's go to 1/2. So let's try x equals 1/2. We'll follow the same process even though we're using a fraction for our division. So 1/2 times 2 is 1. Negative 23 plus 1 is negative 22. 1/2 times negative 22 is negative 11. Negative 16 plus negative 11 is negative 27. 1/2 times negative 27 is negative 27 over 2. Negative 2 plus negative 27 over 2 is negative 31 over 2. Just 4 over 2 plus 27 over 2 gives us negative 31 over 2. And that is not 0, so we know that positive 1/2 is not a solution. So now let's look at negative 1/2. Negative 1/2 times 2 is negative 1. Negative 23 plus negative 1 is negative 24. Negative 1/2 times negative 24 is positive 12. Negative 16 plus 12 is negative 4. Negative 1/2 times negative 4 is positive 2. Negative 2 plus 2 is 0, so we have a solution. So in this case, we're not going to do x plus 1/2 equals 0 because when we write factors, whenever we see something in factored form, we're always using integers or whole numbers. We don't want to use fractions here. So instead, we want to solve for 0 and get rid of any fractions we have. So we'll take our x equals negative 1/2, multiply both sides by 2. So we get 2x equals negative 1, and then add 1 to both sides. So 2x plus 1 equals 0, and now that is our factored form. So anytime we find that we have a fraction as one of our factors, we want to write this using whole numbers, meaning we want to get rid of that fraction, typically by multiplying by the denominator on both sides of your equal sign. That will always get rid of your fraction and allow you to find what your factor is. So now we can rewrite our polynomial as 2x plus 1 times 2x squared minus 24x minus 4. Now let's factor our 2x squared minus 24x minus 4. One thing we can do here is actually factor out a 2. And we want to keep in mind, whenever we're factoring something, we're finding the zeros of that function. So what that means is that we're finding what values for x will make the 0, meaning we need to set this equal to 0. So my first step is I actually want to factor out any numbers that are common to everything in my polynomial. In this case, what's common across the board is 2. So when I factor out a 2, I'm left with x squared minus 12x minus 2 equals 0. That 2 is not going to affect whether or not this polynomial equals 0. So if I want to get the polynomial by itself, for example, I can divide both sides by 2, and I just get x squared minus 12x minus 2 equals 0. So now I can see if this factors. The other reason I want to do this is if we look at our original polynomial, which is f of x equals 2x to the third minus 23x squared minus 16x minus 2, and we look at what we just got as our factored form before we factor any further, which is 2x plus 1 times 2x squared minus 24x minus 4. If I were to distribute my terms and multiply this back out to find my original polynomial, I wouldn't get my original polynomial. I start to get, as soon as I do this first multiplication right here, I get 4x to the third, which is not what I want. I want 2x to the third. So we see that we're double in value here. So I have to make sure that in other places I'm factoring out these terms like this 2 I just factored out, so that when we multiply this back out, we can get our original polynomial, and we can verify that we've factored this polynomial correctly. So now let's see if this is even able to be factored. We'll do our a times our c, which is 1 times 2, which is negative 2. And our factors of negative 2 are 1 and 2. These factors will never add to give us 12, so this cannot be factored further. This means our final answer is going to be 2x plus 1 times x squared minus 12x minus 2. That is our fully factored polynomial. Let's take our next example. This is a longer polynomial, so let's see how this one works out. We have f of x equals 2x to the fifth minus 4x to the fourth minus 7x to the third plus 14x squared plus 6x minus 12. Start with our p and our q. Even though this is a longer polynomial, our process stays the same. Our p is our constant term, which here is 12, and our q is our leading coefficient, which is 2. So our p over q is 12 over 2, and we need to identify the positive and negative factors of each of these numbers. So this is positive and negative 1 and 12, 2 and 6, 3 and 4. And for 2, it's just positive and negative 1 and 2. So all the possible factors are going to be positive and negative 1, positive and negative 1/2, positive and negative 2. 2 over 2 is 1, so we already have that. Positive and negative 3, positive and negative 3/2, positive and negative 4. 4 over 2 is 2, and we've already included that. Positive and negative 6. 6 over 2 is 3, we already have that. And positive and negative 12, positive and negative 12 over 2 is 6, which we already have. So now, let's just work down the line, starting with x equals 1. One times 2 is 2. Negative 4 plus 2 is negative 2. 1 times negative 2 is negative 2. Negative 7 plus negative 2 is negative 9. 1 times negative 9 is negative 9. 14 plus negative 9 is 5. 1 times 5 is 5. 6 plus 5 is 11. 1 times 11 is 11. Negative 12 plus 11 is negative 1, which is not 0, so this is not what we are looking for. Meaning 1 is not a rational root. So let's try x equals negative 1. So negative 1 times 2 is negative 2. Negative 4 plus negative 2 is negative 6. Negative 1 times negative 6 is positive 6. Negative 7 plus 6 is negative 1. Negative 1 times negative 1 is positive 1. 14 plus 1 is 15. Negative 1 times 15 is negative 15. 6 plus negative 15 is negative 9. Negative 1 times negative 9 is positive 9. And negative 12 plus 9 is negative 3. So, again, not a 0, and neither positive nor negative 1 is a rational root. Now let's try positive 2. Again, I know in the last example I went right into the fractions, but we only had 6 possible options, right? Positive and negative 1, 1/2, and 2. So this time we have a lot more. I'm going to stick to our whole numbers going into positive 2. 2 times 2 is 4. Negative 4 plus 4 is 0. 2 times 0 is 0. Negative 7 plus 0 is negative 7. 2 times negative 7 is negative 14. 14 plus negative 14 is 0. 2 times 0 is 0. 6 plus 0 is 6. And 2 times 6 is 12. Negative 12 plus 12 is 0, which is exactly what we're looking for. We know that x equals 2 is 0, which means one of our factors is x minus 2 equals 0. So now we can rewrite our polynomial as x minus 2 times 2x to the 4th plus 0x to the 3rd minus 7x squared plus 0x plus 6. Let's clean up the rest of our polynomial and see if we can factor that further. So we can write that as 2x to the 4th minus 7x squared plus 6. Now this is structured just like our quadratic function, which means we can factor this the exact same way. So we'll take our a and our c, multiply those together, which will get 2 times 6, which is 12. And the factors of 12 are 1 and 12, 2 and 6, and 3 and 4. So in order to get 7, we need 3 and 4. So we can rewrite our polynomial as 2x to the 4th minus 4x squared minus 3x squared plus 6, and negative 4x squared minus 3x squared make up negative 7x squared. So when we factor by grouping, in our first half, we'll factor out 2x squared, being left with x squared minus 2. In our second half, we'll factor out a negative 3, leaving us with x squared minus 2. And our fully factored function here is going to be x squared minus 2 times 2x squared minus 3. Before we bring back our original term, let's see if we can factor these out even further. Looking at both of these, we want to consider our difference of two squares special binomial, and in this case, neither of these can be factored any further. This means our final answer in our fully factored form for this polynomial is going to be x minus 2 times x squared minus 2 times 2x squared minus 3. Time for our last example. If you've made it this far, thanks so much for sticking around, and let's do one more. Always remember, any questions or comments you have, leave them down below. I'm reading and responding to all of them. F of x equals 5x to the 5th minus 15x to the 4th minus 4x to the 3rd plus 12x squared minus 9x plus 27. Our P is our 27 here at the end, and our Q is our 5 here up front. So let's identify all of our terms. We have P over Q, which is our 27 over 5, and our factors of our 27 are going to be 1 and 27, and 3 and 9. Our factors of 5 are just 1 and 5. Meaning all of our possible rational roots for this polynomial are going to be positive and negative 1, positive and negative 1 over 5, positive and negative 3, positive and negative 3 over 5, positive and negative 9, positive and negative 9 over 5, positive and negative 27, and positive and negative 27 over 5. Starting, as always, with our positive 1. So, we brought down our 5. 1 times 5 is 5. Negative 15 plus 5 is negative 10. 1 times negative 10 is negative 10. Negative 4 plus negative 10, negative 14. 1 times negative 14 is negative 14. 12 plus negative 14 is negative 2. 1 times negative 2 is negative 2. Negative 9 plus negative 2 is negative 11. 1 times negative 11 is negative 11. 27 plus negative 11 is 16. This is not 0. Since this is not 0, x equals 1 is not one of our factors. So, let's look at the next one. Bring our 5 down. Negative 1 times 5 is negative 5. Negative 15 plus negative 5 is negative 20. Negative 1 times negative 20 is positive 20. Negative 4 plus 20 is 16. Negative 1 times 16 is negative 16. 12 plus negative 16 is going to be negative 4. Negative 1 times negative 4 is positive 4. Negative 9 plus 4 is negative 5. Negative 1 times negative 5 is positive 5. 27 plus 5 is 32, not 0. So we know that negative 1 is not one of our possible factors, and neither positive nor negative 1 is a valid root here. I'm going to skip 1/5 for now. Let's look at positive 3. We'll come back to that 1/5 if we need to. So starting off, we have 3 times 5 is 15. Negative 15 plus 15 is 0. 3 times 0 is 0. So negative 4 plus 0 is negative 4. 3 times negative 4 is negative 12. 12 plus negative 12 is 0. 3 times 0 is 0. Negative 9 plus 0 is negative 9. 3 times negative 9 is negative 27. And 27 plus negative 27 is 0. So we found our factor. So this means one of our factors is x minus 3 equals 0. And we can start to rewrite our polynomial as x minus 3 times 5x to the 4th plus 0x to the 3rd minus 4x squared plus 0x minus 9. So let's clean up this polynomial that we found, and let's see if we can factor that further. Let's write this polynomial as 5x to the 4th minus 4x squared minus 9. So let's work through this just like a quadratic function. We can take our a and c term, multiply those. So 5 times negative 9 is negative 45. And the factors of negative 45 are 1 and 45, 3 and 15, and 5 and 9. So 5 and 9 are the two factors that are going to add to give us negative 4. So we can expand our current polynomial and rewrite this as 5x to the 4th plus 5x squared minus 9x squared minus 9. And the positive 5 and negative 9x squared give us that negative 4. So, and when we factor by grouping, we'll break this up. In our first half, we can factor out a 5x squared, leaving us with x squared plus 1. In our second half, we can factor out a negative 9, leaving us with x squared plus 1. And this gives us x squared plus 1 times 5x squared minus 9. Now let's take another look. Since we do have these x squareds, let's see if we can expand this further. Our first binomial is not the difference of two squares, so we cannot factor that. And our second one doesn't have two squares. Although 9 is a perfect square, 5x squared is not a perfect square, so we can't factor that further. And our final answer for our factored form for this polynomial is x minus 3 times x squared plus 1 times 5x squared minus 9. Thank you guys so much for watching. I hope you enjoyed and I hope you learned something today. If you have any questions or comments, please leave them down below. You can also find me on Instagram and on Facebook at the A+ Tutor. I upload new videos every single week, so make sure you're subscribed so you don't miss a video. See you next time.